Welcome to this tutorial. In this tutorial, we go through Aspen Plus simulation of a simple ideal Rankine cycle. I start with a short introduction about the Rankine cycle. The Rankine cycle is an idealized thermodynamic cycle of a heat engine that converts heat into mechanical work. The heat is supplied externally to a closed loop, which usually uses water as the working fluid. So as you can see in this picture, we have four main equipments or blocks in a simple ideal Rankine cycle, including the boiler in which we add the heat. We produce superheated vapor. Then we have turbine. The superheated vapor produced in boiler enters to the turbine, expands, and this turbine is connected to a generator usually through a shaft. So we convert this mechanical work via turbine through the generator to produce electricity. After expansion, the liquid and vapor mixture enters to the next block or component, that is condenser. In condenser, the heat is rejected and the mixture of liquid and vapor is converted to liquid. This liquid is further transferred through the next component, that is a pump, to increase the pressure back to the pressure of the boiler. So, uh, if we go through the different processes in a simple ideal Rankine cycle, we can say that from state 1 to state 2, we have a process of isentropic compression. From state 2 to state 3, we have constant pressure heat addition that occurs in the boiler. From state 3 to state 4, we have isentropic expansion in a turbine, and then from state 4 to state 3, we have constant pressure heat rejection in a condenser. Again, these are for an ideal Rankine cycle. If we look into the TS diagram for these four different processes, you can see that from state 1 to 2 and from state 3 to 4, you have two vertical lines because, as we mentioned, these two processes are isentropic. The heat addition and rejection in boiler and condenser, respectively, occurs in the constant pressure. These lines that you see over here, they are constant pressure line. So what happens when you increase the pressure in state 1 to the same pressure of the boiler to state 2? So we jump over a pressure line from point 1 to 2, then we add heat in the boiler, so the temperature rises until we have saturated liquid. Then the saturated liquids, if you add more heat to the saturated liquid, the temperature is constant until everything is evaporated. And from this point, if you add more heat, the temperature rises up to the point 3 in which you have your superheated steam. So do you have three areas here? This area under this bell-shaped curve is the saturation area. Here you have your superheated area, and here we have our subcooled liquid or compressed liquid. And this point is called critical point. So what happens here is that after the boiler, the steam enters the turbine, so the pressure drops because of expansion. And then we have isentropic process, so we have a vertical line. So we jump over this line in the bottom, which is the next pressure line, constant pressure line. Again, the heat is rejected from the condenser, so you have, and since you have a mixture of vapor and liquid, the temperature remains constant until everything is converted to liquid. And at this point, point 1, you have saturated liquid, and this cycle goes on and on. So we have heat addition in boiler, heat rejection in condenser, production of work in turbine, and consumption of work in the pump. In order to calculate the thermal efficiency of a simple ideal Rankine cycle, we can use the equation that is given here. Eta, th stands for thermal efficiency. So eta is efficiency, th is thermal. Eta, th is the thermal efficiency is equal to the net work divided by the Q in. W net or net work is the difference between the work that you produce in the turbine and the work that you consume in the pump. So the difference here is the net work. Q in is the heat that you add in the boiler. So if you divide W net by Q in, you can calculate efficiency. The alternative equation is 1 minus Q out divided by Q in, because W net is also equal to Q in minus Q out. So if you replace this equation on the numerator here, you'll get this equation. So 1 minus Q out, the heat rejected in condenser, divided by Q in, heat added in the condenser, will give you the thermal efficiency of the ideal Rankine cycle. See you in the next video in order to proceed with the simulation of ideal simple Rankine cycle.